Okay, students, in the last part of this lecture, I'm going to talk about an application to something called the orthogonal procrustes problem. I'll describe this problem a bit. This problem occurs in some application domains like computer vision, for example. Now, suppose you have, let's say, two three-dimensional scenes, right? So you have a 3D scene 1 and 3D scene 2. Okay, and let us say that these represent the same object, but the scene has been taken from different orientations, right? So for example, you've taken the picture of the same room possibly, but cameras placed at different locations, right? So this is maybe, so the object is in the center of the room, and this has been taken with a camera placed at one corner of the room, and this has been taken with camera placed at, let's say, another corner of the room, right? And the objective is somehow to combine these two 3D representations to come up with a single richer representation, possibly, right? So essentially what you have here is each point here on this scene is essentially some vector, right? It's a vector of 3 coordinates because it's 3D scene, and here each point is also another 3 coordinates. Okay. Now, suppose I know the mapping, meaning that let's say this point here in scene 1 corresponds to, let's say, this point over here in scene 2. This point corresponds to this point. Okay, maybe this point corresponds to this point in the 3D scene. Maybe this point, some other point here corresponds to some other point here. Okay, but I only know this mapping for a few points, right? I don't know it for all points, and that's reasonable to expect, right? Maybe you have marked a few points on your object. Maybe you are actually measuring the face of a person, in which case you know the eyes, right? So you know where the eyes are located in this scene, you know where the eyes are located in this scene, and hence you can make a mapping. Okay, you can say that, let's say your eye is located here in this position, that is mapped to this position. Maybe here the nose is located and that's mapped to this position, just as an illustration, right? Okay, using this information, I want to obtain a mapping for all the possible points, not just the salient points that you have marked, but all the other possible points. Okay, so essentially the main idea here is to understand. So what I want to do is I want to construct a mapping. Okay, I want to construct a mapping Q such that every point in this scene is obtained by applying Q to every point in this scene. Okay, so the mapping Q relates points of one scene to another. Okay, now since this is basically the picture that's taken from a different perspective, it's natural to assume that your Q is just some sort of a rotation. Okay, because these are you're measuring, let's say all the other parameters are the same, so you're measuring, and the distance from the object is also same for both the cameras, in which case the only thing that's different is the orientation. Okay, it's very natural to make the assumption that the vectors corresponding to the first scene, okay, are related to the vectors in the second scene by a simple rotation or a multiplication with an orthogonal matrix. Okay, orthogonal matrices can correspond to rotation plus a reflection usually, right? So here you may not have reflection, you only have rotation, but for simplicity, let's assume it's a general orthogonal matrix. That could possibly be reflection also. Okay, you can generalize whatever we are going to discuss even to the situation where you only have rotation. Okay, so basically, suppose I record all the vectors in scene 1, all the points in scene 1 as a matrix. Okay, so this is the first point in scene 1, this is point number 2, this is point number 3, so on, right? The number of points will be, well, however many points you have recorded in your 3D scene. Okay, this is my matrix A. Okay, the columns of my matrix A correspond to the vectors in scene 1, right? Similarly, the columns of the matrix B correspond to vectors in scene 2. Okay, what I'm trying to say is every vector in scene A is an orthogonal transformation of the vector in scene B, meaning that A is to be like Q times B. Okay, ideally, right? I put ideally A must be Q times B, right? So when you do Q times B, effectively you are applying you're applying Q to every possible column of B. Okay, I think I made an error in one of the earlier portions of this lecture when I said you apply Q to every row of B, you apply Q to every column of B, right? So you remember that this is like Q times B1, B2 up to Bn. So that's basically QB1, QB2, so on up to QBn, correct? Right. So basically it's like applying the orthogonal transformation Q to every column of this matrix B. Okay, so that's how you get your matrix A. Is that fine? Okay, so that's the main idea, right? The challenge here is that I know both A and B, right? Because I have taken measurements for scene 1 and scene 2, but I do not know Q. Okay, I don't know Q. I want to find Q. Okay, I know A and B. I know that they are related by some orthogonal transformation Q. I don't know what Q is. Okay, let us say that I don't know what Q is, and I want to find Q. Okay, so find the orthogonal transformation Q that makes A to be close to QB. That's the problem. Okay. So it's in some sense, this problem also occurs in some shape fitting contexts. Okay, I just described one potential scenario to you. Okay, so I think this lecture has been really long. Okay, I apologize for that. Okay, so this is so the question is, how do you find Q and how do you even formulate the problem, right? And this gives you the hint on how to go about formulating this, right? So I want to find Q such that A is close to QB, right? In other words, I want A minus QB to be a very small matrix. Okay, so I have to take a norm of this matrix, right? Because I want A minus QB to be a very small matrix, and the easiest norm to analyze is the Frobenius norm. So let's take that. Okay, so I'm not even sure if this analysis is even possible with the spectral norm. Okay, so let's take the Frobenius norm, A minus QB Frobenius norm whole square. Okay, so I want to find Q such that this norm is minimized. Okay, is that clear? Find Q such that A minus QB whole square Frobenius norm whole square is minimized. Okay, so how do we go about this? Well, the Frobenius norm, the beauty is that you can actually write it as a trace, right? So trace of A transpose minus B transpose Q transpose times A minus QB. Correct? Frobenius norm of any matrix squared is a trace of the transpose times the matrix. So you apply that and you get this. So just expand this whole thing out, you get trace of A transpose A minus let me just jump a step and write it as trace of B transpose Q transpose A, okay, plus trace of B transpose Q transpose QB. Okay, now Q is orthogonal. We are only focused on orthogonal matrices, so we can just ditch this Q transpose Q, right, and write Q transpose. So I want to pick a Q such that this whole thing is the smallest possible. Okay, now this does not depend on Q here, the first step, right? It depends on A. A is known, this is a constant. This also doesn't depend on Q, it's a constant. So this is the only part that depends on Q. So effectively I have to maximize the trace of B transpose Q transpose A. Okay, I have to find Q that maximizes the trace of B transpose Q transpose A. Right? Now just to work on this a bit better, what I'm going to do is I'm going to use the cyclic property of trace to sort of isolate Q on one side. Okay, so let me just take so I'll write it as A B transpose Q transpose like this. Okay, there are many ways to write this, but yeah, let's just write it as A B transpose Q transpose. Okay, with the cyclic property of trace. Now I have to maximize this. Correct? Question is, how do you can also write it as trace of Q B A transpose also, if you wish, right? Because trace of a matrix is the trace of its transpose, right? So if you don't like having Q transpose over here, you can take the transpose of this whole thing. You'll get the same thing again anyway. Okay, fine. So maybe we can pick either of them. Right? Let's say we go with this, right? Q B A transpose. So I have to pick an orthogonal matrix Q such that this has the largest possible trace. Okay, fine. So as usual, when dealing with these problems, it's useful to talk of special cases first. right? Now, by the way, I didn't talk anything about the sizes, but A here is an n cross n matrix, right? So it's going to be a 3 cross m matrix if you're talking about 3D scenes, right? So it's going to be like a 3 cross m matrix, okay? And B is going to be another 3 cross m matrix, right? And this BA transpose is going to be a 3 cross 3 matrix, okay? And it makes sense. Q is also a 3 cross 3 matrix that corresponds to the rotation. Of course, you can generalize this to even n dimensions. Nothing special about 3 dimensions. All that you're doing here will go through even for n dimensions, okay? Okay, so you have Q times BA transpose. So now, how do I pick this Q, right? So let's take a special case, as I was saying. Let's assume BA transpose is diagonal. It doesn't have to be diagonal. Let's assume it's diagonal and see what Q we get, right? That may give us some insights. Okay, so if BA transpose is diagonal, so it's like D1, 0, 0, 0, D2, 0, 0, 0, D3. How do I pick my Q? Okay. Now, when you do the trace of this, right? So let's say, your Q will have some entries here. When you do the trace of this, right, you can see that. So Q11, Q22, Q33, and we'll have other entries Q12, Q13, and so on. Right? Let me not write all of them. When you take the trace of this, you will see that you will actually only get Q11D1 plus Q22D2 plus Q33D3. Okay, because remember, trace is like taking an inner product in some sense, right? So because all these other entries here happen to be 0, all these other entries will not actually play a role in the overall trace, right? We'll actually just get this to be a trace. You can very easily check that just by doing a multiplication. Just multiply. Let's say you multiply this with this, these things won't even appear. If you multiply this with this, again they won't appear. And so this will be the trace. Now, if you want to maximize this, right, I want to take each term to be as large as possible, right? Now, what is the largest possible value that the entry of an orthogonal matrix can take? Right? Remember, orthogonal matrix, all the rows, the norm of each row vector must be 1, correct? The largest possible value of any entry is 1. You cannot go beyond 1, right? So ideally, I would like to make each of them equal to 1, the largest possible value, right? So that means I would just try to make all of these entries over here to be 1. Now, if I make all these entries 1, all the other entries have to be made 0. Okay, because to make the norm 1, right, all the other entries have to be made 0. So it's clear that the ideal choice of Q is actually just identity in this case, if BA transpose happens to be a diagonal matrix. Okay. Now, what if it is not diagonal? If it is not diagonal, we will make it diagonal by using some of the techniques that we know, right? If BA transpose is symmetric, you can use the spectral decomposition theorem, but it may not be symmetric, so let me use the SVD, right? So let me write BA transpose as U sigma B transpose. Okay, BA transpose is a square matrix here, so U will be 3 cross 3 orthogonal, V will be 3 cross 3 orthogonal, and sigma will be 3 cross 3 diagonal. Okay, so take the SVD and then we'll write trace of QBA transpose equal to trace of Q U sigma V transpose. Okay, now this is equal to trace of, this by again using the cyclic property of trace, V transpose Q U sigma. Okay, now here is what we've done here, right? So what you have here is a 3 cross 3 orthogonal matrix, is it not? Remember, we discussed earlier, we have orthogonal matrix, product of orthogonal matrix is also orthogonal matrix, right? This is a 3 cross 3 orthogonal matrix and this is the diagonal matrix. Okay, we have already done this analysis where we have an orthogonal matrix multiplied with a diagonal matrix, right? Orthogonal matrix multiplied with a diagonal matrix, we said this orthogonal matrix better be identity to maximize the trace, right? So here the maximum is obtained when V transpose QU is actually equal to identity. Okay, or in other words, I need to make Q equal to V U transpose. Okay, if I pick Q to be V transpose, just get that by just multiplying with V and pre-multiplying with V over here and post-multiplying with U transpose is what you will get. Okay, so this is the correct choice of Q. Okay, that makes A, the matrix A, to be closest to Q times. Okay, so if your model is actually correct, if it turns out that actually this scene is just a rotation of this scene, then you should be able to get the correct Q by using this formula. Okay, all you need to do is find the SVD of PA transpose. Okay. Fine. Of course, I am making a bunch of assumptions here. Primarily, I am actually assuming that the mapping is already known. Okay, that I know which point corresponds to which point. For example, here I know that the first vector corresponds to the first vector here. Okay. Secondly, I am not actually assuming any translation. Right? For example, I said I assume that the object is at the center and the cameras are equidistant from the object. But that may not be a correct assumption, right? In general, you could actually have something like A is a rotation of B plus some translation, right? Meaning that every vector here, so let's say A1 is like a rotation of the corresponding vector in the other scene. So this A1 is vector in scene 1, B1 is vector in scene 2, right? Plus some translation. Okay, and I want to find out both Q and D, for example. Okay, so it's a very interesting exercise. I'll leave you guys to think about it. How do you find the optimal rotation and also the optimal translation? Okay, all you have to do is frame the problem just like you have framed the problem here. Okay, and then use the properties of the Frobenius norm. Okay, and just work out the whole thing. That's it. Basic properties of orthogonal matrices, Frobenius norm, and that's it. Okay. So I think we will stop here. This has been a very long lecture. As I said, I apologize for that. We'll try to cut down some other at some other place. Okay. From the next lecture onwards, we'll begin the discussion on least squares.